Today, I'd like to tell you a little more about the photoelectric effect. This is part of the birth of quantum physics. As we saw, things fell apart in the late 1800s. One of the issues was they could not theoretically reproduce the curve for emission of light from hot objects. Max Planck was able to fudge his way to a solution by saying the energy of the oscillators was quantized. That is, the electrons that were oscillating had to have certain energies, but not others. He came up with this equation, which introduced a new variable h, which is called Planck's constant. Notice this product, hf, on the top of this fraction. He did not know what it meant, but he did know that it was energy. But energy of what? Okay, the second issue was things that gave off light without being hot. Bohr tried to explain this by putting electrons in discrete energy levels. He said these orbitals had angular momentum that was quantized. He had no reason to say this. He also said that the electrons that were in stable orbits did not radiate, but they did give off light when they fell from an excited state back toward ground state. The third issue was the photoelectric effect. This is where light hits a metal and electrons are ejected from the metal. They built elaborate apparatus to study this effect. Before we get into the results, I want to remind you of the old view. The old view of light was that it was a wave, and that the amplitude of the wave told you how bright it was, how much energy it carried. The frequency of the wave told you what color it was. Well, based on the photoelectric effect, we learned that amplitude is not brightness. What brightness is a measure of the number of photons. So light is actually composed of tiny bundles of energy called photons. You can think of them as tiny particles that don't have mass, and that brighter light is going to possess more photons. So when we look at these two red lights, the top one has just a single photon. The bottom one has many more. The bottom one is brighter. Each photon of red light has the exact same energy. So just because it's brighter doesn't mean the photons are more energetic. There's just more of them. They travel at the same speed. They carry the same energy. But the bottom one has more, and that makes it brighter. When we look at different colors of light, blue photons have a higher frequency, a smaller wavelength, so they carry more energy than red photons. They travel again at the same speed. They travel at the speed of light. Okay, so when we saw this, we saw light hitting a metal and electrons coming off. The way we should interpret this, according to Einstein, is light is composed of these tiny bundles of energy, and when those bundles of energy hit the metal, if they have enough energy to knock the electron out of the atom, it will do so. And one photon can knock out one electron, and that's it. So a brighter light is going to give you more electrons being knocked out. But if the photon does not have enough energy to knock the electron out, it doesn't matter how many photons you have. No electrons can get knocked out. It is a 1-to-1 ratio. One photon can knock out one electron. We saw when we did this, the brightness did not affect if they come off. We now know why. We saw that brightness has no effect on the energy. Again, because brightness has no effect on the energy of the photons. Brightness does affect the number of electrons, because as we saw, brighter light has more photons, so more photons will knock off more electrons. Now, electrons that are knocked off by light with a higher frequency are harder to stop, because higher frequency means the light had more energy. If the light has more energy, the electrons knocked off will have more energy. The graph we saw is linear. It has a definite x-intercept. That's called the threshold frequency. It has a slope that is equivalent to Planck's constant. It has a y-intercept that depends on the metal. Okay, so in this equation, the Ke is the energy of the electrons, the Hf is the energy of the photons, and the y-intercept is called the work function. It is the energy required to liberate the electrons from the metal. So what if we used a different metal? We would get the same slope, but we'd get a different threshold frequency. If we trace these backwards, we can see that we also get a different y-intercept, a different work function. Again, every metal has its own work function. So again, looking at the picture, comparing it to the equation, Hf is the energy of the photon coming in. The work function is how much energy it takes to knock an electron off of that certain metal. And then kinetic energy is the kinetic energy of the electron that comes off. You'll notice the formula should make perfect sense. You take the original energy of the light, you minus the energy it took to get off the metal, and that's the energy possessed by the electron. Okay, so these are some questions you should consider. How does brightness affect threshold wavelength? Not at all. How does brightness affect threshold frequency? Not at all. How does brightness affect stopping potential? Not at all. How does brightness affect the kinetic energy of electrons? Not at all. Why? Because brightness does not affect the energy of the photons that are hitting the metal. It just affects how many. So how does it affect the number coming off? Well, if you double the brightness, you'll get twice as many electrons coming off. Okay, frequency, on the other hand, affects the actual energy of the electrons coming off. Frequency determines if they come off, and then if they do come off, frequency will affect how much energy they have. So these little bundles of light called photons possess energy, and they also possess momentum. Light can actually hit an object and give it a push. It can transfer some of its momentum to the object. This is the idea behind what's known as a solar sail.